Okay, friends. Today we continue with Özgür's talk on Einstein-Maxwell manifolds. All right, enjoy.
Hi again. So yesterday we started to work on an example, but before that we need to, as a tool, we need Newman-Penrose formalism, the spin coefficients. We are going to use those. And this metric was our example. By the way, yesterday, due to being hurry, I guess I made some mistakes in some of the indices. So I'm putting the correct ones here. And also we use the direction derivatives in these definitions. And as you may remember, this is our definition for covariant derivative of the tetrad basis elements. Okay. Before going into details of the calculation, I just maybe need to recap, summarize some of the results. And actually, I will give a recipe on how to solve this equation, Einstein-Maxwell equation, for a given metric. Actually, to check if it satisfies the Einstein-Maxwell equation. Let's start from the beginning. This was our Einstein-Maxwell equation, and on the right-hand side, we have the energy momentum tensor, which is made up of, in this case, electromagnetic field strength. These parts we already obtained, so we are just summarizing. And also we have a Maxwell equation, which sets a constraint on the field strength. And symmetrizing the indices. Further, if we have a solution, given a solution, GF, now we use the pair metric and the field strength to these equations. The spacetime will be called electrovacuum spacetime. The spacetime or manifold and electrovacuum spacetime if the electromagnetic field F further satisfies this null condition, or by the Civita pseudo tensor, at a point then the EM electromagnetic field is null at that point. And if a solution GF to the first two equations, for this lecture, I'm going to call this 1 and 2. And if it also satisfies this third equation, null condition, we'll say the space-time is a null electrovacuum. And if it does not satisfy this third condition, we just say the space-time is a non-null electrovacuum. Let's also remember Reinich conditions. Which we obtained before. R is equal to 0, the scalar curvature, and we have we also obtained that one. Equals 0. And for any time-like vector field, say UA, UB, this has to be greater than 0. What we didn't obtain, there's another differential equation which comes from first define an alpha which is inverse and so on from rho sigma r kappa and we have the following differential equation: A alpha B minus B alpha A is equal to 0. Then these algebraic Reinich conditions, which we give by 4, are necessary and sufficient for the existence of a two-form F which satisfies the Einstein equations in 1. And this equation 5, is differential Reinich condition, and it contains 4 derivatives of the space-time metric, and that is also needed for such a 2 form to solve the Maxwell equations in equation 2. Then we also worked on duality rotation. According to this duality rotation, if solves the Einstein equation, Einstein-Maxwell equations, then a rotation G metric stays same, and we apply a rotation by theta. It also solves the Einstein-Maxwell equations, where f theta, let's give this rotation, cosine theta f minus sine theta Hodge dual of f, and theta is a real. And let's also mention Hodge dual. We can obtain like this. And this first equation, I mean, these Reinich conditions also implies, let's write in full sentence, the Einstein equations 1 and the condition 3 for the null case imply that the Ricci tensor is null and positive in the sense that actually we have to do this just differently. We can RAB is equal to 0. And this is equivalent to the statement that the spacetime is a pure radiation solution of the Einstein equations. And in particular, there exists a null vector field which we show by K. As the name suggests, it is null according to definition. Such that Ricci tensor can be shown in this equation. And the integral curves of the vector field K determine a null congruence, and it is this congruence which is uniquely determined by the null Ricci tensor. And the contracted Bianchi identity implies that this congruence is composed of geodesics. Thus, associated to every solution of the Einstein equations with null electromagnetic field is a null geodesic congruence. Maybe I should mention it. Associated to every solution of the Einstein equations with null electromagnetic field EM field is a null geodesic congruence let's show it by C, whose tangent vector field defines the null Ricci tensor. Okay. And given a, or conversely, given a metric with a null Ricci tensor, as in here, let's call this equation 6. Given a metric with a null Ricci tensor, in 6, there exists a family of null two forms whose electromagnetic energy momentum satisfies the Einstein equations. We fix any space-like unit vector field this will not be unique. Any space-like unit vector field SA orthogonal to Ka So since it's unit, we have this, and it is orthogonal to K. Let's say Kb is 0. Then here we define a null two form. Small let Kb as Ka, or let's write open. SA. Which can be shown to be a null two form. And it follows that if we calculate this tensor, I guess you can see what this resembles. It is RAB. Let's give numbers. So the Reinich conditions, algebraic conditions, or equation 6 let's mention that. Reinich conditions or equivalently equation 6 is equivalent Einstein's equation in 1 with a null two form field. Now here we need to just mention that SA, the vector field, space-like vector field we have chosen, it's not unique. So if this the component of two form, coefficient of two form, it's also not unique because it's determined by K and S. And the most general null two form because what was our condition for S is this. It will be unit vector field, space-like unit vector field, and it just needs to be orthogonal to K. And we can find many vector fields like this. The most general null two form whose energy, momentum, tensor equals the Einstein tensor which was the left-hand side of the Einstein field equations. Left-hand side is the energy momentum tensor, is of the form cosine phi FAB minus sine phi whole to FAB. Call this equation 10. And phi is just a function from the manifold to reals. And this local duality transformation represents the freedom in picking the vector field SA. We have given here in equation 7. So to summarize, a null electrovacuum has a null Ricci tensor, which determines a null geodesic congruence C, from which we can build the solution space, this one. Of the Einstein equations. Now we want to impose the Maxwell equation on the family of two forms in this equation 10. Then, in order to do that, it will be advantageous to use Newman-Penrose formalism, and that is defined by a choice of null tetrad. Then, given the preferred congruence C with tangent field K, we define a null tetrad adapted to K to be any extension of K into a null tetrad. Now let's mention here. To summarize, a null electrovacuum let's say has a null Ricci tensor which determines the null geodesic congruence from which we can build a solution space given in equation 10 of the Einstein equations. Which was equation 1. And this part is for the Einstein, to solve the Einstein equations, but we also need to solve the Maxwell equations. So in order to solve Maxwell equations, we employ Newman-Penrose formalism. By a choice of null tetrad. And given the preferred congruence C, with tangent field K, we define a null tetrad adapted to K to be any extension of K into a null tetrad. This should be any choice of null vector fields. Null vector fields such as L, M, and bar, such that the tetrad K, L, M, and bar satisfies the following condition. KA and D -1, or you can alternatively just write KB and D is -1 and GAB is 1. And here you can also write lower index B, M bar upper index B is equal to 1. And with all other scalar products vanishing. All other scalar products, dot products, vanishing. M and M bar are complex conjugated to each other. K and L are real. And our analysis will employ the Newman-Penrose formalism associated to any adapted tetrad. And the results will be independent of the choice of adapted tetrad, and it will be determined only by the space-time geometry. Now we are coming to the differential equations. For that, we fix an adapted tetrad and define as A as 1 over square root of 2 and A plus M bar A. And when we substitute this here, this was our solution, 2 form to the Maxwell equations. Let's give numbers. 11 equation. 12. And we substitute equation 10 into Maxwell equation, because that was our claim. We say that equation 10, the 2 form given in equation 10 solves the Maxwell equations. Which is equation 2. And take components of the resulting equations with respect to the adapted tetrad. And take I see that this has been a little wordy explanation, but this is, as I said, it will be a recipe to find such solutions. So that's why I'm explaining this in detail. Take components of the resulting equations with respect to what do we have in equation 10? Here we have FAB, and FAB is dependent on our choice of tetrad. Here is A. And there exists such phi. Then we express everything in terms of the Newman-Penrose spin coefficients and directional derivatives we defined in the previous lecture. Then express everything in terms of, because when you look at, here we have this Maxwell equation. And when you just write this explicitly, you are going to obtain partial derivatives and Christoffel symbols. And those are related with, let's show it again. We have given them. So they are dependent on the spin coefficients. And we are using those. In terms of the Newman Penrose spin coefficients. And directional derivatives. We have given these definitions. Sorry. And the resulting equations, when we do that, are kappa, this, and sigma of 0, and we also have 1 over I minus 2 epsilon plus rho. These are all spin coefficients. That is also equal to 0, 1 over I plus tau minus 2 beta is equal to 0, and I bar phi plus conjugate of tau minus 2 beta is equal to 0. So sigma was shear, and geodesics were defined by kappa. Let's write it. Thus, a null electrovacuum determines a shear-free which is due to sigma being 0, and geodesic kappa equals 0, null congruence, and given an adapted tetrad, a function phi satisfying here. This phi is the phi in equation 10, this one. I hope we don't have phi in here. Yes, we don't have. So there's no confusion. Determines a shear-free geodesic null congruence, and given an adapted tetrad, a function phi satisfies three linear inhomogeneous partial differential equations. Linear inhomogeneous PD. And then we solve these equations and find phi with the given adapted tetrad. Then we find the solution to Maxwell equation. Let's see if we have everything. Okay, I think we can go on with our example. This is 2W. And so when we calculate the Ricci tensor of this metric, we first calculate the Christoffel symbols, and then Riemann curvature tensor, and by contracting the first and third indices, we obtain the Ricci tensor. And it is actually straightforward. There are not much non-zero, let's see. There are only three non-zero Christoffel symbol coefficients, and only non-zero coefficients is R 1, 1, and that is equal to Wx. Okay. Now, according to how we can we also need to see that its trace are G nu, R nu. It also becomes 0. It's easy to check. And according to our, where is that equation? According to equation 6, we can find a vector field K you can also see that RAB, RBC is also equal to 0. And we also want to find for KA, KB, such a K. So for w square e to the is equal to 4 Ka Kb. Here K the index are same, so R11, so let's say K1, K1. So from here K1 for W e to the Wx. And in vector notation, let's also mention what we are writing. The null vector field K, equation 6, defined in 6, and tangent to null congruence is given by for W e to the Wx, and this is our vector. And now we need to find the null tetrad adapted to this K. The null tetrad, which we show by K, L, M, and bar, adapted to K, is obtained. And what was our, let's see here. These are our constraints. All we are just going to have these scalar products, and all others should vanish. Let's mention. -1 and 1. So K is already found. And L e to the minus Wx u plus I y and m bar just the complex conjugate of this M. Then from this null tetrad, by using these equations, we have these M, K, and all others, and we have the definition of these direction derivatives. Then by using them, the Newman-Penrose spin coefficients spin coefficients for this tetrad is obtained alpha equals beta square root 2 for W, and nu square root 2 . It's a straightforward exercise for you to check these things. The formulas are explicit and we have everything at our disposal. And the rest, let's see what. Okay, let's mention gamma, kappa, lambda, mu, pi, rho, sigma. Sigma and kappa is becoming zero by construction, but the others, I mean this and this one, these are vanishing due to our construction in the first place, but the others are determined from tetrad and the metric. As tau is 0. Yeah, as I said, kappa and sigma vanishing. From that, we see that the null congruence is geodesic and shear free. And rho also, from rho being 0 vanishing, we see that the twist, it's a twist parameter, twist of the congruence vanishes. And the associated foliation of space-time is by the null hypersurfaces, U equals constant. So this this solves the electrovacuum Einstein equation. But we also need to show, we need to find the F2 form. Let's see. So I have some scattered notes. So we need to solve this equation, this partial differential equation 13. We need to solve that and find equation 10, which is solution to Maxwell equation. Okay, now use equations plus 13. Sorry. Equations 13 to compute the electromagnetic field. Is there a question? Okay. We are about to finish actually. Okay, I'm just writing the results, which can be checked easily. We have from equation 13, we obtain these equations are the x phi plus del y phi minus w0, and the last equation partial v of phi is 0, and the general solution to these equations is phi is equal to wy plus a function dependent on u. H is an arbitrary function. Arbitrary function. And we also said there's this choice of a vector field S, and choosing S x. What was the equation number of it? Let's say 7 and 8. And then constructing F via equation 10. we get the null 2 form. W cosine y plus hu e to wx du h dx minus 2w sine, remember it was cosine phi fab here, and Hodge dual u dy sine wy plus hu e to wx du dy. Yeah, so this together with the metric, and it is straightforward to check GF satisfies Einstein-Maxwell equations, and yeah, together we call them the first, let's see, equation 1 and 2. I think I'll stop at this point. Actually, I had the plan to also mention classification of Einstein spaces, like Petrov classification. I don't know, maybe I can put a pre-recorded video for that.
All right.
So I think I'll stop here.
Thank you very much. Any question? Okay, thanks for the nice talk.